Hey everyone, this is 2011 question 4. We did go over this through class, so I'm going to go through this fairly quickly, okay? Some things to note, this is a graph analysis problem. Make sure that you guys know what the graph represents. In this particular problem, it's the graph of f. In other problems, it may be different, so just keep that in mind, okay? Usually, they'll introduce a brand new function that is composed of that graph. So here we have g of x, this brand new function that represents 2x plus the integral of f, which in this case is the picture, okay? So part A, we're finding a few things. We'll start off with g of -3. Basically, if you have g of x and you want g of -3, you're replacing an x for a -3, which is basically what the scoring line did here. Okay, so we know that 2 times -3 is -6. Now, you guys have to understand the context of integration. When you're integrating a graph from one number to the other, you're really just finding the area, okay? Now, notice how the bounds here are a little bit backwards, so we can definitely reverse this. Now, this is just an option. You don't have to do it. Some people can just visualize it from right to left, but I like to just read things from left to right here. So here, we're really finding the area from -3 to 0. So let's go back to our picture here. From -3 to 0, we're really finding the area under this curve, and it's conveniently a semicircle, okay? I'm sorry, not a semicircle, a quarter circle. It's stated in the problem as well, so you guys just have to remember, well, what's the area of a quarter circle? So that's really just -6 minus the area of a quarter circle, which is pi r squared over 4. Now, if you look at that picture and you count the radius from the center, it's really just 3. That's enough to just leave it as is, equal is equal, do the bare minimum, okay? Part A, the second part, they ask you to find g prime of x. That's just the derivative. So the derivative of 2x is really just 2. The derivative of an integral, remember, you just take the upper bound and you plug it in. It's really just the function. Okay, don't worry about that t. It's what we call a dummy variable. It's just a placeholder because eventually the x is going to take over, okay? So we found g prime of x, good. The last part here is finding g prime of -3. So basically, if you know g prime of x, you're going to replace every x with -3. So here we have 2 plus f of -3. Now f of -3, remember, you have the graph of f. So when x is -3, f of -3 is really just 0. It's a location. So 2 plus 0 is just 2. You could leave it as equal if you wanted to, but those are pretty much 3 easy points that you guys can take care of there, okay? Part B, here we go. I noticed right away that we are looking for an absolute max. So right away, I'm looking at a table. X and g of x, because I'm trying to find the absolute max of g, okay? I know absolute extremis could occur at an endpoint. In this case, it's -4 and 3. Or at a derivative, okay? At a critical number. Pretty much the derivative we have right here, we want to set that equal to 0. Okay, now if I solve for f of x, pretty much f of x will equal -2. This gets a little bit tricky when you take a look at the picture. The function has a y value of -2 at about right there. The simplest way to explain this to you guys is anytime it's in between two values, almost always it will be 2.5. They won't give you anything like 2.3 or 2.227. The reason why we can make this assumption is basically because of the fact that it's on a line. Okay, slopes are changing at a constant rate, so it's right there halfway, okay? This doesn't pop up too often, but just keep that in mind. So We know the critical number here is 2.5. In the scoring guidelines, they used 5/2. It really doesn't matter, okay? So you have to go back and plug it in. This is where it takes a little bit of work and analysis. If you're really good at analyzing values, this will save you some time. If not, this will take you some more time, okay? So it's important that we're very efficient on where we allocate our time on this AP exam here. So we know here that at -4, this is going to be 2 times -4 plus the integral from 0 to -4. And I'm not going to write everything out, but basically I got this from my g function right up here, what we started with originally on the upper left-hand corner. You're plugging in -4, okay? The next thing, you're plugging in 2.5. And the next one here is you're plugging in 3. So we're looking for an absolute max. Based on just these values, since 2 times -4 is -8, it's looking very unlikely that that first one is going to be the maximum. So I'm going to just skip that one there. Now here in the middle, I know that 2 times 2.5 is about 5. 2 times 3 is about 6. And this is where the analysis comes in. We have to know what these integrals come out to. So I'll start off with the bottom one here. The integral from 0 to 3, remember, integral is really finding the area. If I'm finding the area from 0 to 3, if you guys noticed, that area is actually 0 because you have the same amount of area at the top as you do at the bottom. So I know this is just going to be 6 plus 0, which is 6. So all we have to do is really just analyze what the integral is from 0 to 2.5. So we go back to our picture. The integral from 0 to 2.5 is just pretty much everything in red here. I don't know the actual value, but I do know that there's more positive area, okay? So because I know there's more positive area, there's a chance that 2.5 could be the max. So I do have to do a little bit of work here. That triangle, I know it has positive area because it's above the x-axis, but the area is 1/2 base 1.5. The height here is 3. That comes out to, oh gosh, what the heck is that? 4.5. Half of 4.5 is 2.25. Okay? The area over here I know is negative 1/2 times. The base looks like it has a distance of 1 and the height has a distance of 2. This comes out to -1. So if you combine those two, 2.25 minus 1 gives you 1.25. So that's the accumulation from 0 to 2.5. So if I go back here, I know that that's going to surpass 6, what we have down here. So I know my x-coordinate is going to be 2.5, which is where the absolute max is going to be. Okay, moving on. Here we go. Your justification, Your justification for part B really is your table. There's no need to explain it anymore. If you guys take a look at the scoring guidelines for B, they explained it a little bit differently. But basically, you have to have a table, okay? So just keep that in mind. Absolute extremos, right away, you're making a table. Part C. Find all values where G has a point of inflection. So right away, the buzzword here is point of inflection for G. So right away, I'm looking at where G double prime is 0. I already have G of G prime. So I know that G prime of X is equal to 2 plus f of X. So the derivative of that, the 2 is going to go away because it's a constant. So f of x, the derivative of f of x is really just f prime of x. Okay? And what we do is we're going to set our second derivative equal to 0. okay? So basically, we're looking for a sign change for G double prime. So if I could show that F prime changes signs, I will know G double prime is going to change signs. So basically, you have to understand that F prime is really talking about the slope of F. So you could do it in two ways. If you understand slope, you could draw mini tangent lines. So for instance, like here, that has a positive tangent line. Or what's even easier is understanding the implications. We know that F prime will be positive if F is increasing. So if you notice, the graph of F is literally increasing from -4 all the way to 0. So here we know that F prime has to be positive, so G double prime has to be positive as well. Now right after, I notice that F is decreasing, so I know that F prime has to be negative, so I know that G double prime has to be negative, okay? But notice how there is a change in signs right about here at x equals 0. Because there is a change in signs for the second derivative of G or the first derivative of F, we know there's a point of inflection, okay? Okay, part D. We want to find the average rate of change of F. Pretty much A-rock, you need 2 points from -4 to 3. So here I have -4, comma something, and then 3, comma something. We don't have the y values explicitly, so you actually have to get it from the graph. I noticed that at -4, the graph of F is -1, and at 3, the graph of F is at -3. With 2 points, you can find the average rate of change. You could set it as equals equal, -3 minus -1 over 3 minus -4. Pretty much leave it there. If you want to use the F of notation, you're more than welcome to, but you don't have to. So the last part of part D says there's no point in part C where the derivative is equal to the average rate of change. Explain why the statement does not contradict the mean value theorem. You guys have to understand that when a theorem is in place, a theorem is proven, meaning it's factual, but every theorem has conditions. So since it doesn't contradict the mean value theorem, that implies that one of the two conditions does not meet for the mean value theorem. So if you take a look, the graph of F is definitely continuous. So it doesn't break that rule, but you notice that it's not differentiable. Okay, most people can identify it at 0 because it looks like a corner and a cusp. But also at -3, there's actually a vertical tangent, okay? But remember, to show why something doesn't work, you really only need to show one piece of evidence. We call that a counterexample, okay? So even if you didn't have the -3, you would still be fine. Just showing that it's not differentiable at x equals 0 because it's a corner or a cusp, that's enough to show that it doesn't contradict the mean value theorem there, okay?